Okay. All right. I think most people here know me, but I'm Aaron, and I've been working on the iOS port of Vanadium and Syncbase since the beginning of the year, which itself has gone through a couple different stages and evolution. And so we were talking a little bit before about kind of some of the confusing points of the way things are structured. And so probably the clearest thing a little bit is if we just start in the Vanadium code base under release Swift is kind of like the big branch point, right? And originally the efforts were mostly focused on what is known as the Vanadium core framework. This is something that's no longer being actively worked on right now, and there are no necessarily dependencies, but it helps set the stage and work out some of the ways that we built this bridge. At core, the main issue that we're trying to achieve here is that we've got this major code base in Go, which somehow needs to be linked into iOS in some kind of way. And as it turns out, there's this wonderful thing called CGo that allows you to take specific functions in Go and export them and make them available to other C, any language or situation that can call on a C-based API. And so in the beginning, a lot of the focus was on how do we take all of these kind of main Vanadium concepts like RPC, like all the security details of principles and blessings and contexts and all that kind of stuff, and wrap it into something where we just take the basic primitives that are available in Go and make them completely bridged into Swift. And so that was essentially the main original focus. And the focus was really on how do we serialize this stuff across in between Go and with C as an in-between, and then Swift on the other side. After the project started shifting directions and Syncbase became the primary focus, there was a renewed effort at creating not just a Swift bridge to CGo and then an Android bridge to CGo that were completely separate, as was the original Vanadium codebase. Android, which had been in the works much, much longer, for example, with Vanadium, they had their own code base, and it was very heavily coupled with Java. So Java, through JNI, which is what is able to talk to C, which is then was able to talk to Go, had that code completely integrated into Go itself. So JNI had its own wrappers via CGo, and the Go code was actively involved in calling this JNI API and creating objects and creating effectively functions that only were useful to Android. Then there was this, meanwhile, this completely separate shift to work on the stuff with Swift, which kind of, Swift by itself not having any kind of JNI type API, which was more generic friendly. And as we shifted to the Syncbase model, as the active development, the thought was, okay, why don't we not try to create something that's specific to any one language, but instead create this generic CGo kind of bridge in Go. So we take all of these concepts from Syncbase and all of the API, kind of abstract that away a bit, and you'll find that, actually I need to launch here, IntelliJ. You'll find that that bridge is in Syncbase. Let me just kind of pull it up and show it a little bit. Should have probably had this already loaded, so give me a second. All right. So under Syncbase, we've got this, which is, you know, under this very long, big directory structure, we've got this kind of bridge thing, and then here the main particular item of the day is the CGo bridge. And so this giant file is basically wrapping the entire Syncbase API. What's particularly nice about this is that it completely abstracts away from Vanadium itself. So Vanadium has a whole kind of init structure, and it's got notions of runtimes and contexts and all of in its own kind of logging implementation. There's all this stuff. The Seago bridge kind of wraps all that kind of stuff, so you don't have to actually know about any of it. It spins up a local instance of Syncbase, which is in the same memory address. It's not a forked process as it might otherwise be able to be done as. And we've got these simple things that allow you to call into it. So, for example, this is just the way Seago works. You see that you've got this kind of function in Go, and above it you've got this / export, and then the same identical name. That is how Seago works to say this function will be exported to anybody who's able to take the static library that we generate and directly can call this init function itself with these parameters. And you'll see that all these parameters start with C dot. That is because these are things that are C data structures that can then be called in here. So essentially, Swift will just call these functions directly, and just to kind of give you some sense of what that looks like, if we go to, say, Syncbase and Syncbase core, this v23 Syncbase init function is just literally called into here from Swift as is. And what's particularly nice about Swift versus something like Java is that we can have this one-to-one mapping of calling in to C without having to jump through any additional hoops, because everything that's available to C is available in Swift. And I'll talk about it a little bit. Part of some of the difficulties that Swift itself has its own notion of structs and classes and its own kind of memory management model. So there is a little bit of bridging that we end up having to do. But more or less, we can directly call these items. And so in terms of the way the current direct development is now with Syncbase, none of it depends on Vanadium core. So that entire framework is essentially on ice until we decide to ramp up Vanadium, like pure Vanadium, versus pure Syncbase, which is kind of two different engineering efforts right now.
So to clarify, if you go and build the Syncbase core project, that includes all of the things that are in Vanadium core. It's just not the API.
Well, it doesn't actually. So what's going on is that Syncbase itself now has Syncbase plus this kind of bridge API takes all of those Vanadium concepts that we're trying to be exposed through Vanadium core and says you don't actually need to go and interact with any of that kind of stuff. We're going to hide all that from you because there's a lot of complexity, and if you're just trying to use Syncbase, you don't need access to that raw stuff. So you don't need to worry about raw serialization of RPCs. You don't need to worry about contexts and forking them with their cancel functions and timeouts and deadlines and all that kind of stuff. We're going to take care of all that for you in the Go code, and all of that's going to be behind the scenes in terms of this Seago bridge, and so now what we're going to do is take that abstraction layer and kind of more or less one-to-one it into Swift, and that's in Syncbase core.
But in the Go code, like Swift, Syncbase still depends on Vanadium,
yes,
and so you're getting all the Vanadium goodness.
Right.
It's just that you've got a higher level API through Syncbase. So
right.
From the Swift code, like the current implementation is you just use Vanadium by using Syncbase. But
exactly.
The code's in there, like if in the future we decide that we want to expose something,
right.
we could just add something in this Seago bridge and it could be called.
Well, so if it needs to call direct to Vanadium stuff. And so I think part of the issue here was that if we wanted to build this kind of Seago or the Syncbase stuff with Vanadium, we would have a lot of code that was specific into the bridge in Swift, where it's calling things through the Vanadium layer, and then it's calling into Go, and then we'd have to replicate a lot of that if we want to do that in Android. And there would be a lot of complexity exposed to Swift and Android if we wanted to directly talk Vanadium stuff. Instead, by kind of shoving that all into Go, where a lot of the Syncbase efforts are already being done anyway, we don't have to worry about that bridge. We can do all the complicated stuff in Go and then expose this nice kind of abstracted high-level API that then Android, Swift, some other new platform comes out, whatever it is, can then have that stuff already dealt with, and have a simplicity to it in terms of the way that it works. Because if you're working with SyncBase, you then at that point don't need any of the raw Vanadium concepts, even though SyncBase itself is built on top of all these Vanadium concepts. We can kind of hide all of those from you, because there's a lot of different concepts that are going on that can be a lot to learn and have to and kind of non-trivial to program against. So moving on a little bit, so we've got this kind of SyncBase core. That SyncBase core framework is essentially more or less a one-to-one wrapping that brings all of these functions that we have in Go that we're exposing, like login and collections and databases and reading and writing rows from them. And it says, okay, we're going to take all of those C functions, we're going to get the data out of them that's in this kind of generic C defined data structures, and we're going to translate it into Swift. And so what you'll see in, say, for example, in the SyncBase Go is that we've got this like lib.h, and in here you'll see things like v23 SyncBase string, right? And it's the struct that has a character pointer and a variable that represents the length of this string. Well, these are C structs, and so these aren't really particularly useful to Java or to Swift. It's a little inconvenient to use. It assumes that you already know that everything in here needs to be UTF-8. You need to know what P and N are, all this kind of stuff. And it's not obviously the most convenient to work with when you're working with a higher level language. And so what we get out of something like SyncBase Core is to say, okay, this will have something like types.swift that will have in it a way of wrapping things like string that will say, okay, we're going to be able to take these strings, we're going to take this data structure, we're going to use this kind of really nice language feature that Swift has called extensions that allow us to take these C data structures and allow it to convert it into what you're used to working with in Swift, which is just the predefined string that Swift comes with. And so it's going to handle all of these things where it goes ahead and is able to convert, say, like a string and allocate memory via malloc, and if something can't be converted to UTF-8, then it's going to go ahead and worry about that condition and free the stuff and throw exceptions and all that kind of stuff. So all of these data structures in this in-between thing, types.swift is able to go ahead and translate these data layers in between, and now we have this kind of common way of being able to go to Swift data structures and C Go, or these C data structures that then Go can kind of consume. And so all of these things that you're seeing here in SyncBase Core, like collection and database, these are all basically Swift taking that Go set of concepts and now translating them into their Swift equivalents. But it's still more or less one-to-one. So if we kind of scroll down a little bit, you see something like we've got our database class, which maps to the kind of database structs that we have in Go. And you'll see most of these functions are literally just calling a single function. So for example, create here ends up just calling this v23 SyncBase DB create, which if you go back to our impl.go, you'll see is just a function in Swift or in Go that still is more or less a one-to-one calling into the Go SyncBase code as well. And effectively, all that's happening here is that we're taking Swift data structures, we're translating them into CGO-based data structures and C structures using our conversion factors. It then is able to take that in. Again, these are all C things. You'll see these cname.extract. What that's doing is the kind of equivalent thing in Go. We've got this types.go thing that's able to take, and using also a similar concept to extensions from Swift, we take this thing that was a C data structure, we do a bunch of different stuff, effectively copying it into Go, freeing the underlying data structure, and then returning something that Go can understand. And now it continues on in kind of Go land, now that these things are proper Go objects. And so that's really at its core what sync-based core is doing. It's just simply defining the data structures in Swift, creating a bridge into CGO, and then CGO itself takes those structures, converts them back into Go, and then communicates back and forth. And just kind of one little note here, you'll see a lot of, they're all doing this kind of v-air maybe throw. Go itself has this notion of v-air, which is this kind of way of dealing with exceptions and errors. It is a very kind of rich way of doing things, so it can tell you, okay, what is the error, what's the stack trace, maybe there's some more information we have about it. We are able to capture all that stuff going into Swift. And the way that that works is you got a very particular calling convention that we're doing in Go, which is to say all of the things that are normally passed in to Go when you call it, which is generally things are one way. It's Swift calling Go. There's some exceptions to that, but for the most part, it's Swift calling Go. We're going to do all those kind of normal arguments where you just directly pass these data structures. They're not pointers at all. They're just the struct itself that's kind of a pass by reference. The exception is anything that we'd want to return. So, for example, if we have an exception, we need to essentially return that back to the other side. We don't do normal returns, especially because a lot of times we may be wanting to return multiple things. Instead, those are all pointers, effectively. And so what we've got here is this pointer for potential v-air struct. In C, that would be, if we have an exception, you can see here, this would be kind of us. Okay, I don't know exactly what's going on there, but this is an error coming back from calling into the Go code itself. This is saying, okay, error wasn't null, so then we're going to take this structure and we're going to fill it out and then return right away. And so what's going to happen is, on the other side, we've got this call into CGO. We've got this structure that's been allocated, and we have a pointer to it, and we're going to go ahead and pass that. This generic function is then going to catch all of those. So you see this maybe kind of throw thing. You can see here what it's doing is it creates the v-air struct. It's got memory to hold on to it. It's then going to go ahead and call into the block we kind of passed the pointer. You can see here this kind of passing the pointer to the struct. It's going to go ahead and be available to be called in, and in the end, if we see that this is essentially non-nil, and we're able to convert this thing from this C-based v-air data structure into a Swift one, then we're going to go ahead and do a proper Swift throw. And so now we've kind of bridged into Swift-based exceptions. And we're going to be able to take that and we're going to pass it to something called sync-based error, where we've now starting to catalog all the different potential errors. And we're going to consume these v-errors themselves and convert them into this kind of higher level sync-based error. And so every single function call into Go more or less does that to be able to handle errors. So that's a very kind of rough skim of how that works. So that's kind of the sync-based core layer, and that's what we refer to as the sync-based low-level API. And then on top of that, we've got our sync-based framework itself, right? And that sync-based framework depends on sync-based core to be talking to Go. Sync-based itself has no notion that there is Go, that all that stuff is wrapped, and instead just calls directly into sync-based core and kind of wraps all that stuff and does some higher level logic to make it a little bit more user-friendly. So we've got notions, for example, of things like permissions and blessings being handled for you to a degree, that we've got these kind of notions of default blessings. So sync-based itself has a very expressive notion of security and who can talk to whom through blessings. The low-level API exposes that. So if anybody wanted to that was more advanced, that wanted to build something on top of that, they could. But recognizing that most people, at least in the beginning, won't, the higher level API sets same defaults for kind of everything and makes it even more simplified in terms of the way it works. And is also able to then deal with some of the callbacks and threading models and all that kind of stuff. That's still kind of raw in the way that's exposed in the low-level API. Again, the high-level API abstracts away all that and makes it very Swifty, so that an ordinary Swift developer doesn't have to think twice about what they're using, doesn't even have to recognize that there's Go in there at all, and it's blocking-based thread model. Instead, everything kind of seems typical in terms of the way that they would expect it to. So I'm going to pause for a second because you guys, I imagine, might have some questions right now.
So the sync-based core code reflects what the Go code is like. Does the high-level API in sync-based also reflect the high-level efforts in Go, or is that a separate concept?
Is there actually? I actually don't know. Is there a high-level Go API?
When we use the term high level, we usually refer to the Java side.
Yeah, I think. Okay. Well, maybe Adam can answer this.
There's no implementation of the high-level API in Go right now.
But
right now there isn't.
All right, so this is a focus to make the mobile development easier and more idiomatic, with the effort that the high-level API would feel right on the platform it is, as a preference to matching each other. So
as well as implementing certain logic that may otherwise be tricky and difficult.
Right.
So it does things like, for example, this notion of user data storing all the sync groups that somebody might be a part of, and then whenever something is inserted into that, it automatically tries to join that kind of logic is implemented at the high-level API. So that way, the low-level API allows you to have maximum flexibility and expressiveness. You can use sync-based itself kind of however you want, and then we have this notion of how we think you're likely to want to use it, and that itself is expressed in the higher-level API. So we may do things like, for example, have a lot less errors in exception, aka exceptions, at the high-level API. That's something that I think Emin's going to be working on a little bit. My guess is the sync-based core would not do that. We would still have all the potential kind of lower-level APIs, all the exceptions available in the low-level API. Once you get to the high-level API, maybe you only have 5 different potential errors. It's based upon the ones that we know will be thrown by these things in order, because we've also confined to what these things can even be in the first place, right, by setting what your permissions would be or whatever it is.
You mentioned that most of them are blocking calls. So is there any asynchronous calls left?
So the way that the thread model works is that Go has a notion of Go routines, right? And so you typically write code in Go that's blocking, but it's inside of a Go routine, and so you've got this kind of threadlet or green threads or whatever it is kind of model, so it's fine to block. Well, it's not actually fine to block in Java or Swift, in particular on the main thread, because you'll freeze up everything if you do so. And so the way that we deal with that is things that we know are going to be blocking, like anything that involves the network. So for example, when you log in, right? Currently that login, you pass an OAuth token that you received from the Google Sign-in SDK. That then has to go out and call some server to exchange that OAuth token for the blessings for your device. That's a network call. That's therefore blocking. We use the existing background queue that Swift via Grand Central Dispatch provides. So Swift in Grand Central Dispatch has this notion of queues, which is basically like a thread. And you can create as many queues as you want, which is like creating as many threads as you want. They provide certain ones by default, so they provide you the main queue, which is what all the UI is done on, and then they provide you these kind of background queues that are also what's known as concurrent queues. So those queues can accept many different requests to execute things in parallel, and then it kind of, behind the scenes, figures out how many processors it has, and then figures out however many it wants to do. We essentially jump to one of those threads, do the blocking call. Then when we get the result back, we then have a user-specified queue that defaults to main. So if you don't do anything, it's the main queue. We then kind of dispatch onto that queue the callback. And so these functions, so for example, if we go to the login, is probably the simplest example of this. You'll see here that in Swift, when you log in, we take your OAuth credentials, and then you also pass a callback. And that callback is just an anonymous function that says we're going to give you a potential error, and you're not going to return anything. And so that way, when you call login, you're always passing the callback. And you can see here, actually, if we look at the code, this is exactly what it does. It's very simple. We first get onto our background queue. We then call all of our blocking things. And then when they're done, we then call back on our sync-based queue, which is the result, basically. And then that's very thin. So that's basically how everything works in terms of asynchronous behavior. Most things are not asynchronous. Most things are meant to be fast in the way that they're implemented, which dramatically simplifies the way things work. So the majority of calls are not blocking. The other kind of exception to the way that this stuff works would be, say, callbacks for like watch or scan, where it's calling you. So there's very few things where Go calls Swift. Most of the time it's Swift calling Go. And generally the way that that works is, so if we look at, for example, something like watch. Okay. This is a little bit hairier in the way this works. Give me a second to kind of explain this, but essentially what we've got is this generic pattern where we've got this function in Go. So let's take a look at the Go code. It takes a couple different parameters, but the main important thing is that it itself takes function pointers in a struct called callback. So if we look at this struct in lib.h, you can see here we've got a couple different function pointers for things like onChange and onAir. So these are things that Go would be calling into Swift or Java, and that takes a couple different parameters. But the most important one here is we've got this sync-based handle. That sync-based handle is essentially a void pointer. It's just like stick whatever you want in here. The struct that you pass to Go, you're going to give it a handle, and then Go's going to pass that same data back to you. And what that allows you to do is write functions in these kind of functions that the function pointers will point to that are kind of context-free, right? They're kind of these static functions that are more or less global, and all the context is being passed to it by this handle that you gave it in the first place. And so the reason why we do that is if you look here at the way that we define this struct in Swift, so here I'm defining this callback, right? With a C function, for it to be safe with Swift, these functions can't actually capture via closure any context. The Swift compiler will not allow it. It can only create these functions if they themselves are completely contextless and everything's being passed to it, and it doesn't close on anything. And so what you're seeing here is that we've got this kind of anonymous function, and Swift is fine with that. It can create this single C callback that's kind of global when you do that. And it's just calling, it doesn't have to do this, but it does it just for simplicity, into this kind of static function on watch change. You can see it's just passing essentially the parameters it got, which is the handle that we see here, and then the watch change, which is also what's being defined here, right? So to be able to kind of recompose this back into the context that you had when you called this in the first place, right? So we've got this watch function that the user called. It's going to return a watch stream. It's very specific in the way it works. Well, all of that context in terms of the way that it's working we're going to kind of shove into this watch.handle class. And so this is the general pattern that we're using. So if you look at watch.handle, we've got, this one in particular is a little bit more complicated in the way it's working, but in general, that's capturing all of the local context. And what we're actually going to do is hand that object to Go. Now, Go doesn't really know that we're handing it this proper Swift thing, and in terms of memory management, Swift doesn't normally work this way. Swift kind of handles its own memory management through ARC, which is basically automatic reference counting, but it has this very nice, for us, API called unsafe, or unmanaged, rather. That's a kind of unsafe way of dealing with things. And so what we can do is we can, via unmanaged, we can get essentially a pointer to this object through this particular function call, where we say, okay, take this object, this handle object that we just allocated. Pass retain basically means give me this unmanaged object with a +1 reference count. So the normal Swift reference count is now +1. So when this leaves scope at the end of this function, it's still going to stay in memory. And now hand me, to opaque means give me a pointer to that. We're going to take that pointer, we're going to get a data pointer through this casting to an unsafe mutable pointer, and then we're going to pass that to Go as our handle. Now you see this kind of unsafe bit cast into a uint. That's from a bug in Go that Razvan managed to trace down, which was to say, if we actually made this a void pointer, it's not going to work. So instead we have this uint pointer that's basically the same thing. It's just a number. So we're going to take that pointer, cast it to a uint, and then we're going to hand that off to Go. Now when we get our call back from Go, we're going to get that memory address. We're going to say, okay, take that memory address, make it this notion of the C opaque pointer, pass that back up to managed, and then managed is able to take that address in memory, cast it to a watch.handle, which is our proper class that's encapsulated all of the object, and then depending upon the callback, something like onWatchChange, which is being called many times, we still want to keep that as a +1. We never want to change the reference count to that, so we're going to take an unretained value to that, which is to say this particular handle right here has no additional +1. It's just at whatever the reference count is, and then we're going to pass that off to our final function in Swift that's now dealing with this change and calls back to the user. And then when it's finally going to be dead on a error function, for example, we then take a retain, which means now -1 that thing, and Swift will handle freeing it after this function call because it's now at 0 reference count. So that's the very big, strange song and dance that we do to deal with callbacks from Go into Swift.
Between two garbage collected languages with different.
So that's also, yeah, I mean, that's something to be considering here, right? It's like there's all this complexity because we've got Go wanting to manage all of its memory and Swift wanting to manage all of its memory. So something I kind of glossed over in the beginning in terms of the copying is like, how do we do this stuff beyond the kind of callback functions, even just the straight, how do we hand a string from Swift to Go? Well, the general rule that we worked out is to say, whenever you call a function, you essentially malloc memory in C for that. The receiver will then grab that and free it. So you never free. You create it. The receiver is now in charge of that memory and it can do whatever it wants. And to be safe, we always copy currently. So there's a bit of an inefficiency here, and as we progress and determine that certain things, like for example, anytime we deal with data that could potentially be big, that we have the luxury of being careful with who's calling what and be careful about that kind of stuff. But the main difficulty that will always involve a copy is that Go itself has a copy of something, and when it wants to, and it's kind of its own memory managed way, we can never just pass a pointer to that directly to the other language. It's not possible because that violates the C-Go boundary rules, which is to say you can never pass a Go pointer, Go memory address. And the reason being is that Go's garbage collector is a moving garbage collector, so that memory address is not stable. You can never pass that to something else. It is completely in charge of that world. So there's always going to be, at least in terms of something that originated in Go, going to be one copy to get it out of Go, and we can't avoid that. It's just not possible. We can, however, do something that we allocated in Swift. We can hand to Go and do that in a zero-copy way, although currently we do these copies always. And so you'll see that these extract functions in Go are doing exactly that. They're copying the data that it got and then freeing the original pointer that it was given and then returning the Go value back out of it. And we're doing the same thing in Swift. Next question.
Well, following that, have you tried doing a get on a really large value, like say like on megabytes or something like that? I mean, does that involve a copy?
Yeah, that would. Everything involves a copy.
But is that something that could be optimized away to not have a copy?
So again,
you don't know how much size.
There's always going to be a copy coming from Go. The only way that we, to my knowledge, could avoid that is if we use some kind of shared memory scheme, using like some kind of, and that's going to be platform specific, where if Go is able to put something in a shared, and I actually don't know if this is even true, but if Go is able to make it available through some kind of shared memory that then Swift could directly call in a zero-copy way, that would be a potential way of doing that. But even that, I don't know if the APIs are zero-copy for that kind of stuff, because you do have that moving GC. And even a network call, that may be platform specific, but my guess is maybe a network call, if we did some kind of like local Unix pipe, maybe Go supports that in a zero-copy way.
Does iOS have Unix domain sockets?
Yeah. So Swift is just a language. Currently, all the platforms it supports, which is Linux and Darwin, are all Unix in terms of having, or POSIX at least, and so they have access to name pipes. Any other questions as it stands? Okay, so something that you guys had asked before in terms of what works and what doesn't work, what to expect about the current kind of state of things. So Vanadium core is very rough in the way that works, in that it can initialize the runtime, it can initialize logging, and has this notion of contexts. All of that kind of stuff works. It's pretty nice in the way that it ties into being Swifty. RPC to a degree works, but the big missing piece is VDL and VOM. So VDL is a little bit like JSON. It's a way, or maybe a protobufs is a better actually analogy. It's a way of describing an interchange of data, and which then something like Swift or Go or Java can generate classes given a description of data in VDL. And then there's VOM, which is to say, okay, given this description of data and some data, how do I put this into something that I can then send over the network, right? So that's more like JSON, right? So, or what protobuf eventually does, right? It encodes it into something. So VDL is like 80% done in its code gen for Swift. It went up to the point where VOM more or less is required to be implemented. We don't yet have VOM at all, and that's something that ideally we're starting on soon. And some of the work in Go, in terms of simplifying it in the new version, will make that easier to do. Once we have that VOM port to Swift done, that means that we could then finish the VDL code gen, which then means the easier RPC functions that are generated as part of VDL in terms of the server client RPC stuff would then be able to be implemented, and at that point, Vanadium Core is in a pretty good place, actually. That's all on pause. Syncbase itself does also use VOM. So Syncbase, in terms of the high-level API, right now is largely done. We're now kind of doing the finishing bits and making sure that works through building these example apps. But in terms of the specification, the high-level API, I think it's actually all done. That may not be completely right. Maybe it's like 95% done, but it's plus 90% done. The part that's largely missing to make this be able to interop with Android, which does have VOM, is VOM. And so the kind of compromise right now is that you can use Syncbase, but what you're putting in and out of these rows is just raw bytes. It's up to you to figure out what that means. If you want to use JSON, if you want to use protobufs, if you want to use some other thrift or whatever it is, that's up to you. And if on the other side on Android, you're also using thrift or JSON or protobufs or whatever it is, then you can then decode these raw bytes and it'll work. And we'll have interop between Android and iOS. Once we have VOM, we then have a much simpler way to be interacting with Syncbase. Because what that will mean is that we're going to automatically be able to serialize a lot of basic types for you. So everything that you could put into Java or into JSON, right? So ints and bools and dictionaries and arrays, there's a VOM equivalent for as well. And that means that you can take your Swift array of ints and just pass it to put. And it will automatically be able to say, okay, this is a data type that I can serialize because it follows what we call the Syncbase convertible, or probably will be called VOM convertible protocol. And we have implementations for arrays of ints, and we'll convert that to VOM, and we'll put that into Syncbase for you automatically. And then that will then be a very easy way to interact with it in a interoperable way across all the different platforms that we support.
I have a question.
Sure.
So as you say, Syncbase stores normally right now the payloads as VOM. It also intercommunicates between other Syncbases using VOM and VDL.
Right.
So if you don't have that in iOS, how can that talk to another Syncbase?
So what is happening is that it is still VOM. It's just the VOM feature that allows you to store raw bytes. So VOM allows you to take a byte array and encode it into VOM, and so that is actually what's happening behind the scenes. So Swift hands Go raw bytes. Go then which has VOM, takes that raw bytes, encodes it into a raw byte array in VOM, and then puts that into Syncbase.
Oh, so at the Sego level, it does all that. It's only at the kind of the user interaction level or the developer interaction level, it doesn't have it.
Right,
Okay.
exactly.
All right.
And so is it the case right now if I were to use, so the get and put API in Syncbase just takes bytes.
Right.
And so if I were to write an app that had the same format for those bytes, they would interop between Android and iOS right now.
So for example, when you serialize out JSON, that's going to give you an NS data, which is just raw bytes. We take that NS data and happily store it for you. If Android on the other side, you're going to have VOM, but if you take that VOM and it's going to give you like whatever the Java equivalent is of byte array, you can then take that byte array and hand it off to Jackson or whatever your Java-based JSON library is, decode that, and now you can use JSON happily to interop.
So for interop with the Java currently takes Java POJOs, and encodes them in VOM, right?
Right.
So is the set of data structures that Java can handle, will there be like a one-to-one mapping with the types of Swift data structures? Or is there like is there could you is it possible to encode a Java data structure that would be impossible to decode in Swift, or vice versa?
Well, so because VOM itself has its own data types that it supports, it's up to every language to find a way to map with that. VOM actually has notions of certain things that Java doesn't have, right? So VOM has a notion of sets, I believe, that
Right.
or
Yes, it is. Yeah.
wait,
As unions, one thing. It has unions, which Java doesn't have.
If you
okay, so
want to interop today between Android and iOS, then you can't read and write POJOs in Java.
But there's a Java API to write bytes, and you could do that.
right.
Yeah, if you pass to the Java API objects which are byte arrays, and so they get treated as VOM byte arrays, and then you do JSON encoding on the Android Java side before you talk with the sync-based high-level API, then it should work. As long as you use the same JSON encoding and decoding in Android and iOS so that you're not losing information.
So the Java Mojo encoding is just using like Java serialization or something like that.
It's using VOM.
Oh, it is using VOM.
There's code in Java that represents these POJOs as objects in VOM.
Oh, okay.
Representing all the types of the fields and the structs and such.
Right.
Okay.
And so eventually, hopefully, relatively soon, on the like 1 to 2 month scale, Swift would then also have that as well. And so then it would be really easy in terms of that interop in between. And because VOM itself has its own specifications in terms of what it supports, just like you can't encode anything arbitrarily into JSON, JSON can only support certain kinds of data structures and types. VOM's the same. We'll have a story for however that maps from VOM to Swift, and then that would be how you do the interop between Android and iOS.
And some of the stuff that we're figuring out right now is like, we're building these examples for tutorials so that people can start playing with this. Like, how much do we build apps that do something as an interim, and how much do and when do we wait? And
so also just something I want to touch on. Oh, go ahead.
How much do we really want to focus on VOM for Swift?
So it's 2:20. What I want to do is like not have that conversation as part of this meeting, and wrap like the sort of like this is what the code does today conversation.
So sort of relates to that. I've been saying Android, and then I say kind of Swift, and these are kind of not analogous things, right? Because Android is all written in Java, and Swift is just a language. It can run on theoretically Linux. So what of this is cross-platform, right? The intention with all this stuff has always been targeting iOS. That said, there's almost nothing about the code that's iOS specific. It's almost all just generic Swift. So it should be the case that this stuff just compiles if you want to create a Mac app or you want to create a Linux app. What is not the case is the build system is geared towards that. So the build system right now is all geared using Xcode for iOS. It's probably not very difficult to make it also be able to target these other things. It's a little bit of a different story when you talk about something like Linux that doesn't have Xcode. I think Swift itself as a language is still working on that story in terms of how it works, the open source version on Linux, and its own kind of package management and all that kind of stuff. Right now, we're not using any package manager. This is not CocoaPods friendly, all that kind of stuff. It's not going to be too much work to get it to be there. That is just a task to be done. Right now, it's just very simple, focusing on kind of Xcode, iOS, at a minimum deployment level of 9.0. Part of the reason why that's also the case in terms of 9.0, in terms of the iOS, is that I think this changes in Go 1.7, which is not yet out. Until then, Go's compiler cannot generate position-independent static libraries on 32-bit ARM, which is to say, like the iPhone 5 and below is a 32-bit processor. Because it can't do position-independent code, Apple will not allow that on the App Store. That's a requirement for iOS. Is your code, any code you compile has to be position-independent code. They're probably doing that for security reasons. The Go compiler is not able to generate that. Therefore, it's not possible. I think that changes in Go 1.7. iOS 9.0 was the first version that allowed you to say, you can deploy an app that's 64-bit only. And you can specify that in your entitlements. Luckily, at this point, it's something like 85% penetration, maybe 90% penetration in terms of 9.0 on devices. So you have automatically broad market share when you're developing for it, but it means that anything you write is only 64-bit only. The other related gotcha is that at some point, Apple is going to require everything that is submitted on the App Store to also include what's called the bit code. We have the lower level LLVM code, not the final compiled binary. Because we are using the Go compiler to generate the static library for the Go code instead of LLVM, it is not generating bitcode. So right now, they're okay with not shipping your apps with bitcode. At some point, they're going to flip a bit, and that's no longer be the case. I believe that there is work that's being done right now.
I want to
sorry.
Let's not speculate about the future.
Okay.
We have these caveats. I really appreciate this presentation and walkthrough. We might cut this into smaller sections that that highlight different parts of the architecture and share them with the mailing list. But yeah, let's. We're just about end of time.
Okay.
So I'm going to wrap this meeting, and you can continue the conversation about what the code does right now on the external mailing list, and then we can continue speculating about the future amongst ourselves.
Sure.
All right. Thanks, everybody.
Cheers.
Bye.